Okay, folks. Let me begin with, again, a reminder of some announcements. Number one, today I am going in class, I am going to go over enthalpies of reaction from enthalpies of formation. I'll also briefly mention how enthalpy is related to stoichiometry. Then we'll be moving on to gas laws. My goal today in class is to introduce the gas laws through the ideal gas equation. But then in lab, I plan to continue that lecture and get into how the ideal gas law is related to molar mass, how the ideal gas law is related to density, how you can figure out stoichiometry with the ideal gas law, and then get into Dalton's law of partial pressures. All of this is leading to the end of new material as of today. Once I finish the lecture in lab, you will complete the lab itself. And then at the very end, I have that lab, the ideal gas law lab, is due on Monday. On Tuesday when you come to the exam. Now, before you leave today in lab, though, I will have one page that everybody must complete. That is part of, it's not going to be part of your grade. It is going to be an assessment piece, but I need you to take it seriously. And so it will be related to the ideal gas law and density. After that, on Tuesday, we'll have our fourth exam. And then if all goes well on Wednesday, we will be doing nothing but a review of how to study for the final. As of yesterday, I think I have everything but the thermodynamics lab, which is due today, the gas law lab, and exam 4, as far as things I have to physically grade, they're in the books on Blackboard. I plan to release 2 columns this morning. Column number 1 says total points with 4 exams. Basically, and that one I've given a letter grade to. Basically, that is going to tell you where you stand. Now, it's not going to be complete until I finish all the grading I have to do. So it's still not complete. It just tells you where you stand as of today. It will continue to change, though, through the time I finish grading your exam next week. The other one, it says grades with 3 exams. That column assumes a dropped exam. It means you're taking the final. It is the column that you will use to determine what you need to make on the final to get an A, B, C, D in the course. Using the fact that you need 1,000 or 900 points for an A, 800 points for a B, 700 points for a C. I will release those 2 columns, but they're again not going to mean as much until after I get your grades finished. So don't freak out about them, but know that they're assuming a dropped, for the 3 exams, it assumes a dropped exam grade, it assumes a test grade or a lab grade dropped, it assumes all the grades have been dropped. So those 2 columns are going to continue to change until I get your grades for next week done. But once they're done, it will tell you where you stand in class. Exactly. So I just wanted to let you know I'm going to release those two. Any questions for me? And I will also upload all of the video lectures, all of the Zoom lectures as of today's, hopefully during my little break today. Okay, well, if there's no questions, then we're going to get into today's information. At the end of Tuesday, I introduced the enthalpy of reaction from enthalpies of formation. The symbol for the enthalpy of reaction that we'll be using is delta H of reaction naught. And the symbol for the enthalpies of formation that we'll be using is delta H of sub F naught. Enthalpies of formation is the enthalpy associated with the formation of 1 mole of compound from its elements in their standard state. So for instance, to form 1 mole of water, we would need to react 1 mole of H2 gas with 1/2 mole of O2 gas, and that has an enthalpy around negative 242 kilojoules per mole. Whereas with the formation of butane would require us to react 4 moles of carbon solid with 5 moles of H2 gas to form 1 mole of C4H10 gas. Now, these are called the enthalpies of formation because with respect to the elements themselves, the enthalpy of formation for an element in its standard state is equal to 0. So there is no enthalpy of formation associated with H2 gas, O2 gas. So that negative 242 is strictly associated with the H2O gas. There is 0 for an enthalpy associated with the carbon solid. There is 0 for the enthalpy associated with the H2 gas. So that negative 125 kilojoules per mole is strictly associated with C4H10 gas. Now, as a reminder, the naught symbol in delta H naught of reaction and delta H naught of formation, the naught symbol just means that these things are done under standard conditions. And standard conditions are 1 molar for an aqueous solution, 1 atmosphere for gases, and 25 degrees Celsius for everything. So again, this is just a recap of what I was discussing at the end of Tuesday. Any questions? So we can use these enthalpies of formation to calculate the enthalpy of a reaction. And the way you do so is delta H of reaction under standard conditions is going to equal the sum for the products of the delta H of formation times the number of moles minus the sum over the reactants for the delta H of formation times the number of moles. Hit the wrong button this morning. Folks, you're going to see this reaction not only this semester, but you're going to see this reaction this equation this semester, and you're going to see this equation in college chemistry too. When you get to the Gibbs free energy chapter. So you're going to see this again. So let's just look at how we use this stuff. Let's say I have I want to know delta H of reaction for N2O gas plus NO2 gas going to make 3 NO gas. And we're going to give the delta H of formation in kilojoules per mole for NO gas is 90. For NO2 gas, it is 34. And for N2O gas, it is 82. So our delta H reaction is going to equal our products. There are 3 moles of NO times the delta H of formation, which is 90 kilojoules per mole, minus the reactants. There is 1 mole of N2O times 34 kilojoules per mole, plus there is 1 mole of NO2. Oops, N2O is 82. NO2 times 34. With this equation, you will notice that the moles cancel out. And therefore, you're going to be left with kilojoules for the delta H. So when you do this math, you get a positive 154 kilojoules. Now, we haven't really discussed the meaning of enthalpy. When you have a delta H that is negative, it is spontaneous or favorable with respect to enthalpy. A positive delta H is non-spontaneous or unfavorable with respect to enthalpy. A negative delta H is considered to be an exothermic reaction, meaning that heat is generated as a product. Whereas a positive delta H is an endothermic reaction, which means heat is a reactant. Essentially, what all this means is that under the spontaneous or favorable reaction, if heat is a product, it means that once the reaction gets going, it goes. Or it continues spontaneously. Whereas an endothermic reaction means that heat must continuously be added to the reaction to make it occur. So looking back at our previous problem, with a positive delta H of reaction, that means that this is an endothermic reaction. Heat is a reactant. And heat must continuously be added for the reaction to occur. Questions? Let's look at one more example. Determine the delta H of reaction for two H2S gas plus three O2 gas going to make two water liquid and two sulfur dioxide gas. Given Given the following pieces of information. For H2S, it's a negative 20.1 kilojoules per mole. For H2O liquid, it's a negative 285.8 kilojoules per mole. And for SO2 gas, it's a negative 296.1 kilojoules per mole. In the table that I have, it doesn't give me O2. Why? Because it's zero. It's an element in its standard state. So some tables will not give you elements in their standard state, others will. By the way, before I get into it, on active, I think you're going to be given the enthalpies of formation. But on the optional homework, you're going to have to be prepared to look up the enthalpies of formation. If you have a textbook, it is in the back of the textbook in one of the tables. If you don't, just type in enthalpies of formation table on Google, and you'll find a table of enthalpies of formation. Or type in the substance and enthalpy of formation. You'll get it. So to do this reaction, it's going to be the delta H of reaction, and I'm going to be writing rather small, is going to be equal to 2 moles of water times negative 285.8 kilojoules per mole plus 2 moles of sulfur dioxide times negative 296.1 kilojoules per mole minus 2 moles of H2S times negative 20.1 kilojoules per mole plus technically 3 moles of water times 0 kilojoules per mole. So your delta H of reaction, when you key this into the calculator, comes out to be equal to a negative 1,123.6 kilojoules. I meant, no, it's supposed to be oxygen. Thank you. Now, that means that it is exothermic. Oh, goodness. Turn on my brain. It is exothermic. It means that heat is a product. And it means that once this reaction starts, it continues spontaneously. Questions? Yes. This goes back to the original equation. Where the enthalpy of the reaction is equal to the sum being plus over the products minus the sum over the reactants. So we add the products together, we add the reactants together, but we subtract the reactants from the products. Other questions? That's all there is to enthalpies of formation. And you will be given the enthalpy of formation. And you will be given the equation on your equation table or equation page. The big thing that you have to memorize that will not be given to you is this information. And then knowing how to use the equation. Other questions? We now move into the last chapter of new information. Folks, this chapter really begins your journey into information that you will pick up in college chemistry too. Let me explain what I mean by that. At the very beginning of the semester, we learned about the atoms of the elements. We learned about the number of protons, the number of neutrons, the number of electrons. We then went on to understand where the electrons resided in the electron cloud using quantum numbers and electron configurations. After we had a thorough understanding of the atom of the element, we then moved on to combining these atoms of the elements to form molecules. And we formed ionic compounds and we formed inorganic covalent molecules, along with the alkanes, which are organic molecules. After we started naming those, writing the formulas and naming those compounds, we then went on to learn about what they looked like. So we developed the Lewis structures for those compounds. We then applied the Lewis structures to VSEPR theory to understand the shape of the molecule. We applied the Lewis structure to valence bond theory to understand the hybridization that must have occurred on the central atom in order to obtain the shapes that VSEPR predicted. After we got a thorough understanding of our molecules, we then went on to start combining these molecules to form compounds. And when we did so, we combined these molecules and we in a balanced chemical reaction in order to follow the law of mass conservation. Now, with respect to those balancing of reactions, we performed some stoichiometry with them, but going back to the reaction itself, we learned to predict the products of a precipitation reaction and an acid-base neutralization reaction. We learned how to take that balanced chemical equation and come up with a complete ionic equation, which would describe what everything truly looks like in solution. And then we went on to combine that, or to go to the net ionic equation, which showed us what actually is undergoing a change in reaction. So all of this has been about the equation itself. And now, and we also talked about redox reactions. Now we've applied enthalpy to that story as well, because if we're going to tell the complete story using a balanced chemical equation, we not only had to have the balanced reaction and understand the state of matter associated with the reactants and with the products, understand what was going on, but we had to apply energy to this story. Now what we're going to do is you're going to back up a little bit and you're going to get into more detail about those compounds. And the first bit that we're going to get into is going to be gas laws. So we're going to take all those gas molecules and we're going to get a thorough understanding of gas molecule behavior. When you get into college chemistry 2, the first thing you're going to do is you're going to take those liquid compounds and you're going to get a more thorough understanding of liquid compound behavior. And after that, you're going to get into solids and get a more thorough understanding of, potentially, depending upon who you have, get a more thorough understanding of solid compound behavior. And then you're going to get into aqueous solutions again, and you're going to get a more thorough understanding of aqueous solution behavior. After that, you're going to get into kinetics. So, which is the first bit of a story that you really want to apply, which is, at what speed does the reaction occur? After kinetics, you get into a equilibrium and you discuss to what extent does the reaction occur. So it all goes back to about the reaction, starting with kinetics. Does it occur? I mean, how fast does it occur? To what extent does it occur? And then you get into thermodynamics, where you apply this enthalpy equation again, and you're asking yourself, does it occur in the first place? And then you get into some electrochemistry, and depending upon who you have, nuclear chemistry. So we're starting another story piece today that you're going to use when you get to college chemistry 2, because we're discussing gas behaviors. And then when you get into college chem 2, you're going to discuss liquid for certain, aqueous for certain, and maybe solid behaviors. So, gas laws. There are some things that we can say about gases. One is that gases spread out to fill whatever container is available. What this means is that the volume of the gas equals the volume of the container. Secondly, gases move in every direction applying pressure to the container upon collision. Basically, folks, this makes sense if you think about a balloon. You put gas into a balloon. The gas molecules are going bing, 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 bing. And as they bounce off of the balloon, they're keeping that balloon blown up by applying pressure to the container. The third thing, if we're talking in an ideal gas, collisions of the gas molecules are elastic. Basically, it just means that they're going to come in, they're going to collide, they're going to bounce off of each other and move in another direction. So what it means is that in an ideal gas, reactions do not occur. Essentially, what that means is that the moles, the total moles of gas is going to equal the moles of gas 1 plus the moles of gas 2 and we can continue. Four, the temperature in Kelvin, always must be in Kelvin, impacts the speed at which the molecules move. This all comes into play in the kinetic molecular theory. Because what is kinetic energy? Energy of motion. And if you look at the majority of these comments, they all involve motion. The other thing I want you to note from what I've been describing is the volume of the gas, the pressure of the gas. the moles of the gas, and the temperature. These are the four factors that we use to describe a gas. They will be the volume, which we will represent with a capital V. It'll be typically in milliliters or liters. It'll be the pressure, which we describe with capital P, which will can be in units of atmospheres, torr, millimeters of mercury, inches of mercury, or pascals and kilopascals. In other words, there's a variety of units, and in the video lecture, I give you the conversion factors for these units. You'll also have the conversion factors, I believe, in the lab for today, and I'll discuss some of them as we go. Your next thing is moles of gas. Which will be in a lowercase n. It's always going to be in moles. And then you have your temperature of your gas. T, which is always going to be in Kelvin. That's the only acceptable temperature unit. For a gas. Okay, so gas laws, we have a variety of them. There is Boyle's law. Which says that pressure and volume are inversely proportional. When temperature and moles are held constant. It is P1 V1 equals P2 V2. There is Charles' law, which says that the volume and temperature are proportional when P and N are constant. It is V1 over V1 over T1 equals V2 over T2. There's Gay-Lussac's law. Which is pressure and temperature are proportional. When volume and moles are constant. So it's P1 over T1 equals P2 over T2. There's Avogadro's law. Which says moles and volume are proportional. When pressure and temperature are constant. So you have N1 over V1 equals N2 over V2. You have the combined gas law. Which combines Boyle's and Charles' law. Which is P1 V1 over T1 equals P2 V2 over T2. With all of these, the key to this for your exam is simply understanding the relationship. You're not going to have mathematical calculations over it. The first one you're going to have calculations over is the ideal gas law. It's the first one that takes into account all four variables. It takes into account pressure, volume, the moles of gas, and the temperature. But it introduces one more piece, and that is the ideal gas constant. R. Now, if you look up R, you can find R with a variety of units. The one I'm always going to use is 0.0826 atmosphere liters per mole Kelvin. I'm sorry, it's 0.08216 technically. Folks, this ideal gas constant is going to be your dictator of units. It's going to tell you what unit you must use for pressure. It's going to tell you what unit you must use for volume. It's going to tell you what unit you must use for moles. And it's going to tell you what unit you must use for temperature. It is the dictator. You must follow the dictator. So let's look at a couple of examples. If I have 4 moles of gas at a pressure of 5.6 atmospheres and a volume of 12 liters, what is the temperature? I start my gas law problems the same way I do a lot of problems, by identifying pieces of information I've been given. I have been told 4 moles of gas. That means that N is equal to 4 moles. I have been told that the pressure is 5.6 atmospheres. I have been told that the volume is 12 liters. And I have been asked for the temperature. If you notice, you have all 4 variables. All 4 variables means that you're going to be using PV equals nRT. But in order to do this, I need my R, which is 0.0821 atmosphere liters per mole Kelvin. Now, because I need 0.0821 atmosphere liters per mole Kelvin, it's the dictator. I need to make sure my units match. My pressure needs to be in atmospheres. It is in atmospheres. My volume needs to be in liters. It is in liters. My amount needs to be in moles. It is in moles. So in other words, all my units are matching. So because all my units are matching, that makes this easy because I can simply rearrange this equation to solve for T. So PV over NR is equal to T. And then it becomes a plug and chug affair. So pressure of 5.6 atmospheres times volume of 12 liters divided by N, which is 4 moles, times R, which is 0.0821 atmosphere liters per mole Kelvin. And that is going to give me my T in Kelvin. So this T comes out to be equal to 200. No. This T comes out to be equal to 204.63 Kelvin. So I would have done the same thing with the other gas laws had I used them. I always do the same process. Number one, I identify what I was given, and I identify what I want to solve for. That typically is going to tell me which equation I need to use. In this case, I needed to use the ideal gas law because I had PV in and I was looking for T. I had all 4 variables. The ideal gas law is the only one with all 4 variables. But with that, I also needed R, which told me what unit everything needed to be in. So I would have done all my conversions to make all my units match. Then I rearranged my equation and I'll plug and chug. So let's look at another example. If I have an unknown gas at 1.2 atmospheres in 31 liters at 87 degrees Celsius. How many moles of gas do I have? Okay, so again, identifying what I was given and what I want to solve for. I was given 1.2 atmospheres. So my pressure is 1.2 atmospheres. I was given 31 liters. So my volume is 31 liters. I was given 87 degrees Celsius for my temperature. And I was asked to solve for moles of gas. So I need to know N. Seeing that I have all four variables, that means I'm going to be using the ideal gas law of PV equals nRT. But and in order to do so, I need the ideal gas constant of 0.0821 atmosphere liters per mole Kelvin. Again, this is a dictator. So looking at this, my pressure needs to be in atmospheres. It's in atmospheres. That's good. My volume needs to be in liters. That is in liters. So that's good. My temperature needs to be in Kelvin. It's not in Kelvin. So the first thing I need to do is I need to change this temperature by adding 273.15 to the system to get the new temperature, which comes out to be 318.15. And now my units do match. And so I can use that. Once you've got your units matching, we rearrange this thing to solve for the desired variable. So PV over RT is equal to N. P is 1.2 atmospheres. V is 31 liters. R is 0.0821 atmosphere liters per mole Kelvin. And T is 318.15 Kelvin. Yes. 360. Sorry. That's what I get for looking at somebody else's work. So I'll calculate it myself. So the answer comes out to be 1.25 for my number of moles. Actually, 1.26. Of gas. Questions? Now, we can use this information to solve for some stoichiometry. Given the reaction, two C8H18 plus 25O2 goes to form 16 CO2 plus 18 H2O. What volume of oxygen is needed if 4 moles of gasoline are burned at 0.953 atmospheres and 35.0 degrees Celsius. Okay, let's look at what I was given. I was given 4 moles of gasoline. So I have 4.00 moles of C8H18. I was given a pressure for oxygen. Well, a pressure, let's just say a pressure of 0.953 atmospheres. I was given a temperature of 35.0 degrees Celsius, and I was asked to solve for volume of oxygen. C8H18, I can't use those moles, and it's not just ready, it's not ready for PV equals an RT yet. Because I'm asking about the oxygen, not the C8H18. So the first thing I need to do is I need to get the moles of oxygen. And I can do that with some stoichiometry. Four moles of C8H18. According to the balanced reaction, there are 2 moles of C8H18 for 25 moles of oxygen. So there is 50 moles of oxygen. Now I can use PV equals an RT to solve for the volume. But to do so, I'm going to need my R of 0.0821 atmosphere liters per mole Kelvin. And I'm going to have to make sure everybody matches up. So my pressure needs to be in atmospheres. It's in atmospheres. My volume needs to be in liters. That's what I'm wanting to calculate, actually. My amount needs to be in moles. It's in moles. And my temperature, though, needs to be in Kelvin. So I'm going to have to convert that temperature because it's not in Kelvin. So that temperature in Kelvin is equal to 308.15 Kelvin. Now everything's in the correct unit. So I'm going to rearrange this to solve for volume. So that's volume is equal to nRT over P. And then I can just plug and chug. So volume is equal to 50 moles O2 times R, which is 0.0821 atmosphere liters per mole Kelvin, times my temperature in Kelvin of 308.15, all divided by the pressure, which is 0.953 atmospheres. So we get $1,327 liters for our gas. Okay, we are going to pick up with a variation of the ideal gas law in lab, where we are actually able to calculate density, molar mass, and stuff like that. And then we are going to deal with Dalton's law of partial pressures, which is associated, all of this is associated with the lab and with the item that will need to be completed at the end of lab. I will see you this afternoon, or morning for some, I guess.